Alrighty, in today's lesson, we're going to look at chapter 5. We're going to start with 5.1, talking about probability of distributions. In our first objective here, we're going to learn how to construct a probability distribution for random variables. So a variable, as a review, is a characteristic or attribute that can assume different values. A random variable is a variable whose values are determined by chance. Discrete variables are variables that can have a finite number of possible values or an infinite number of values that can be counted. Alrighty, I'm going to try to put this all at once before I have to scroll up, but it says variables that can assume all values in the interval between any two given values are called continuous values, meaning all the decimals and stuff can be counted. Continuous random variables are obtained from the data that can be measured rather than counted. All right. So that's a kind of a review of what we've seen in the first 4 chapters. All right, probability distributions. Is a process that leads to well-defined results or outcomes due to chance. A discrete probability distribution consists of the values which a random variable can assume and the corresponding probabilities of the values. The probabilities are determined theoretically or by observation. So what that means is we can say if you roll a die, you have a 1/6 chance out of each one of them, or we can roll the die 10 times and say, hey, we got 1 4 times, we got a 3 2 times, and we got 1 1 time, whatever the concept is, and we can use that data as well to get a probability distribution. So let's look at our first example here. So this example is based on theory, what should happen versus what actually might happen. So in example 1 here, probability distribution for tossing 3 coins. We're going to construct a probability distribution for a discrete random variables using a probability experiment of tossing 3 coins. So here we go. So this is what should happen. So if you toss 3 coins, you have these as options: tail, 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 head, tail, head, tail, head, tail, tail, head, head, tail, head, tail, head, tail, head, 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 head. All right, those are the, I believe, 8 different options that you can get with 3 coins being tossed. If X be the random variable of the number of heads, then X assumes values of 0, 1, 2, or 3. So here we go. So basically, again, X is the random variable of landing on head. So you can either land on head 0 times, 1 time, 2 times, or 3 times. So no heads, 0. 1 head is 1. 2 heads is 2. 3 heads is 3. So these are the options that you can get. And out of those options, to get a tail, 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 there was 1/8 probability. To get either tail, tail, head, tail, head, tail, or head, tail, tail, each one had a 1/8 probability. To get a head, head, tail, head, or a tail, head, head, each one of those had a 1/8 probability. And to get all 3 of them as a head is a 1/8 probability. So to get 0 heads is a 1/8 probability. To get 1 head, we actually see that we have a 3/8 probability. To get 2 heads, we see we have a 3/8 probability. And to get all 3 of them as heads, we see that we have a 1/8 probability. So as we work through this, we then take those probabilities and now we can go to our chart. So what we can see is, again, 0 was 1/8. So 1/8 chance of getting the probability. Then we have a 3/8 chance of getting heads, 1 head, a 3/8 chance of getting 2 heads, and a 1/8 chance of getting 1 head. So what I'm trying to do here is to find the probability of doing all of this. Well, I guess before I continue on, this is just how you make a table. We'll take that to the next step to find the probability that we would get ahead using this information. All right, but for now, that's where we'll stop, but we will take that one more step further. Let's look at example 2. Probability distribution for rolling a single die. So we'll construct a probability distribution for rolling a single fair die, no loaded die here. The sample space for a single die, again, is either a 1, a 2, a 3, a 4, a 5, or a 6, and with each outcome having equal probability of 1/6. So if it's a fair die, each one of these probabilities have a 1/6 chance of happening. And again, for right now, that is all we're doing. We will take the next step eventually. And it's not a hard step. I want to go ahead and do it, but this will follow with the book. All right. So that's what should happen. These are events that if a fair coin is tossed or a fair die is rolled, these are the things that should happen. You can also complete one of these tables based on observation. So I can still roll the die or flip the coin and then tally what actually happened to produce a chart like this. Now, on this one, we're going to look at example 3 of the number of World Series games. So the Baseball World Series is played by the winner of the National League and the American League. The first team to win 4 games wins the World Series. In other words, the series will consist of 4 to 7 games, depending on individual victories. The data shown consists of 40 World Series events. The number of games played in each series is represented by variable X, so either 4, 5, 6, 7. So we're going to find the probability, which is P of X, probability of how many games in the World Series for each X, and construct a probability distribution for the 40 World Series, including the winner was determined in 4 games 8 times, 5 games was 7 times, 6 games was 9 times. In the last 40 years, the world's determined games for 16 times. So to do this, the probability of getting it 4, and in observational purposes, we saw it happen 8 times out of 40. We saw then that there were 5 games 7 times. We saw that there were 6 games 9 times, and we saw that there were 7 games 16 times. So then if you take all of these and you just type them in the calculator to get a decimal, there was a 20% chance that the game World Series would be 4 games. There was 0.175, so there was a 17.5% chance that the game would be 5 games long. There was a 0.225, so there was a 22.5% chance that the World Series would be 7 games long, or a 0.4, meaning there was a 40% chance that the World Series in the last 40 games would last 7 games. All right, so that's a way we can do it in observational. So we can do theoretical, or we can do observationally. What actually happened versus what should happen. Process isn't too much different. All right, requirements for a probability distribution. The sum of the probabilities of all events in the sample space must equal 1. Meaning, if I was to, let's do this better. If I was to add up all of these different probabilities, I should get 1 as my total. The probability of each event in the sample space of the probability must be between or equal to 0 and 1. Either I have a 0% chance of it happening, or I have a 100% chance of happening, or I have it in between those. So as a formula base, I should have 0 less than or equal whatever each probability is, less than or equal to 1, meaning whatever the probability of that event happening is between 0 and 100%. Should not go anywhere else with that. And then over here, the last statement here is the sum of the probabilities of all events must be equal to 1, since the sample space includes all possible outcomes of the probability experiment. We don't take anything away. All right, and this will be the last statement. And then, of course, I'll break this up just like I did last time into a video for each section. All right, so here, the probability of any individual event must be a value, again, from 0 to 1. A probability cannot be a negative number or greater than 1. All right. And then in the next video, obviously, you'll see we'll talk about mean, variance, standard deviation, and expectations. See you in the next video.